Hi, Mr. Causey here. Now you recall that in the last video we were looking at complex numbers that lay on the unit circle. So if we have a complex number a plus ib that has a modulus of 1, that means its distance from the centre, from the origin, is 1, then we can write it in the form cos theta plus I sine theta. And obviously we'd have A being cos theta and B is sine theta. So this is called the polar form, and theta is an argument of z. Now, arguments are not unique. We could add or subtract multiples of 2 pi to get different arguments. But that's essentially what we were doing in the previous video. So how do we extend the idea of polar form to numbers that are not just on the unit circle? Well, it's useful to consider that each complex number is associated with a corresponding vector. So for instance, if we have a complex number z1, a1 plus I, b1, then its associated vector would have components a1 and b1. z2, a2 plus I, b2, its associated vector a2, b2. Now it's a very simple matter to add two vectors together by adding their corresponding components. And likewise, this means that the two complex numbers associated with these vectors can be added, and the real and imaginary parts correspond to these components. Negative z2, well, it has an associated vector negative a2, b2 for the components. The negative of that has components negative a2, negative b2. And that means negative z2 as a real part, negative a2, and an imaginary part of negative b2. And that therefore leads us to the fact that z1 minus z2, which we can think of as z1 plus the negative of z2, and you think of the associated vectors there, we have a1, b1 for components, plus negative a2, negative b2 for components. Adding these two vectors gives us a1 plus negative a2, that's a1 minus a2, and b1 plus negative b2, that's b1 minus b2, and therefore the difference of these two vectors, a real part a1 minus a2, and the imaginary part is b1 minus b2. So the associated vectors allow us to do geometry with these complex numbers, just as we've seen here. So how does all this help us to find the polar form of a complex number that lies off the unit circle? Well, it involves looking at a scaling. So if we're looking at a vector, a complex number z, real and imaginary parts a and b, and look at the corresponding component, then doubling that vector, we know that that scales the vector by a factor of 2, and the corresponding complex number 2z would have real and imaginary parts 2a and 2b. We could scale it by a factor of 3. Look at the corresponding vector, 3 times that. Components 3a and 3b, so the real and imaginary parts of this complex number would be 3a and 3b. We could even scale it down by a scale factor of 1/2. The vector shrinks, and the corresponding complex number would have real and imaginary parts of 1/2 A and 1/2 B. So let's go back to all the complex numbers that lie on the unit circle and imagine that all their vectors, corresponding vectors, multiply by r, where r is greater than 1, and we get this enlargement of the circle, and then multiplying all the corresponding vectors by r less than 1, we get a shrinking of that circle. Let's try and gather these facts together to see if we can work out the polar form for any complex number z. Suppose we've got z a plus ib. So step 1, that would be to find the modulus of z. And we do have a method of doing that, square root of a squared plus b squared. And suppose that's r. And also we would find theta. So we calculate the modulus and also find theta, which is an argument of z. Now recall that any complex number on the unit circle has the form cos theta plus I sin theta. So if we look in particular at the complex number on the unit circle that has the same argument as z, its associated vector has components cos theta sin theta. So what we can do is to scale that vector by a scale factor of r, that's the modulus of z. Doing that gives us a vector associated with z. And that vector has components r cos theta and r sin theta. So we're ending up with z having real part r cos theta and imaginary part r sin theta. So there's our step 2. That's the crucial step. Step 2, we scale the corresponding point on the unit circle, that's cos theta plus I sin theta, by a factor of r. So that leads us to the following definition. If we have a complex number x plus iy, we can write it in the form r times cos theta plus I sin theta, where r is the modulus of z and x is r cos theta and y is r sin theta. Now a couple of things to note here, that the argument theta is not unique. We could add or subtract multiples of 2 pi to that. Also the x equals r cos theta, y equals r sin theta can be rearranged, and this is sometimes useful. We'll find this useful later in determining the argument. Cos theta is x over r, sin theta is y over r. So it's time for some examples, and I would suggest at this stage you stop the video and attempt all of these examples, and then we'll take a closer look at the solutions. So let's tackle example 1. Complex number -2, -2i. We have to write it in polar form 2 different ways. So let's first of all have a look at where it is on the diagram. It has a real part of -2 and an imaginary part of -2. And let's have a look at its modulus. So we take the real part and square it, and the imaginary part and square it. And the result of that calculation, square root of 4 plus 4, square root of 8. Now remember 8 is 4 times 2, that would be square root of 4 times the square root of 2. 2 root 2 is it simplified. And then the argument, to go all the way around to pi plus another pi upon 4. So it's 4 lots of pi upon 4 plus another 1 pi upon 4. That would be 5 lots of pi upon 4. And therefore, writing it in polar form, it's modulus times cos 5 pi upon 4 plus I sine 5 pi upon 4. Now, an alternative way would be to measure the angle clockwise. Now, the modulus is going to be the same. This time, we've got negative 3 lots of pi upon 4 for another argument of that complex number. So there's the two ways that we can write z in polar form. Let's tackle example 2 part A. We're asked to find 3i in polar form. Let's again locate it. Now the real part's 0, imaginary part is 3. So its modulus, it's the modulus of 3i, would be the square root of the real part squared plus the imaginary part squared. Well, this should come as no surprise if you think about it. Square root of 9 is 3. Looking at that diagram, you could have told that the modulus is 3 because that's the distance. It's very obvious the distance of that complex number from the origin is just 3. Its argument, if we go anti-clockwise, is pi upon 2. So the polar form of 3i, remember 3i is the Cartesian form, the polar form is its modulus 3 times cosine pi upon 2 plus I sine pi upon 2. That's not the only form. There are other arguments, for instance 5 pi upon 2 or minus 3 pi upon 2. So next up is the polar form of negative 1 plus I. So again, let's look at where it is. Real part, negative 1. Imaginary part is 1. So the modulus, the square root of the real part squared plus the imaginary part squared. Square root of 1 plus 1 is 2. And an argument, 3 pi upon 4. So the polar form, or one of the polar forms, be root 2 times cos 3 pi upon 4 plus I sine 3 pi upon 4. So let's tackle the last question where we're given a complex number in polar form. 2 root 2 times cosine negative pi upon 4 plus I sine negative pi upon 4. Now where is that on a diagram? Well, we know one of its arguments is negative pi upon 4, so it will be on a line from the origin that makes an angle of negative pi upon 4 with the positive x-axis. We also know that its modulus is 2 root 2. So it's a distance from the origin of 2 root 2 along that line. So we can pin it down. So how do we write this complex number in Cartesian form? Well, what we can do is find the exact values of the cos negative pi upon 4 and the sine negative pi upon 4. And remember, looking at the diagram, that the real part is positive and the imaginary part is negative. And we do know in the fourth quadrant that cosine's positive and the sine's negative. Now we'd get our exact values from a square of side 1. Pythagoras would tell us the diagonal is root 2. There's our pi upon 4. So exact values, the cosine of pi upon 4, that's positive pi upon 4, is 1 upon root 2. And the cosine of the sine of pi upon 4 is also 1 upon root 2. So we can proceed in evaluating this. The cosine of negative pi upon 4, remember that's a positive value, it's the same as 1 upon root 2, and sine of negative pi upon 4 will be negative 1 upon root 2. The imaginary part is negative, fourth quadrant sine is negative, so that will be minus 1 upon root 2 times I. And we can proceed by multiplying out. 2 root 2 times 1 upon root 2, the root 2's cancel, leaving us with 2 times the 1, minus 2 root 2 times the 1 over root 2 again, the root 2's cancel, leaving us minus 2i. So that would be the Cartesian form of this complex number z. And if you look at the diagram, we pinpointed it, and it certainly looks reasonable that the x coordinate and the y coordinate are 2 and negative 2. Real part's 2, the imaginary part is negative 2. So that's Mr. Corsi signing out, and hope you enjoyed the video.